All right, so welcome to this long-range colloquium. And my name is Babak Saraja of Indiana University. If it's your first time joining us, just a quick intro to Virtual Science Forum that organizes this series. It's a volunteer-run and open initiative to facilitate online scientific events like this one. If you would like to help with this effort, you can join us. All of our content is open and online. You can go to our website and join us there. I also would like to thank Kavli Institute of Nanoscience Delft for their support of this effort. Just a quick reminder also that we'll be taking a break in 2 weeks' time, and we'll come back on December 9th with another colloquium, which will be the last one for this year. All right, so today we have Jennifer Cano of Stony Brook University talking to us about higher magic angles in twisted bilayer graphene, a very hot topic. And thank you very much. Jennifer, go ahead.
Great. So this talk has two parts because I had kind of two projects that I'm excited about. So we'll see how the two parts works out. In the first half of the talk, I will talk about the chiral model of twisted bilayer graphene. And in particular, what we're doing is looking at higher beyond the first magic angle, and we can actually make a connection between higher magic angles and higher Landau levels, which gives a hint that there could be some really interesting interacting physics going on there. In the second half of the talk, I will switch gears and talk about a generalization of twisted bilayer graphene that we've been thinking about, which is dubbed topological twistronics. What happens if you apply a moire superlattice to a Dirac cone on the surface of a TI, as opposed to the Dirac cones in graphene? What are the similarities and differences, and can we get flat bands out of that? And I'll also say, I'm not really gonna watch the chat, so I think people can ask questions during, if you want to, either way is fine. So briefly before getting into physics, I will just say I'm looking for a postdoc, and if you have, the job information is down here, but if you have a question, you can also email me about this position. So, so both of the projects that I just mentioned are motivated by twisted bilayer graphene, and I think by now it doesn't need that much introduction. So I will just say that why is twisted bilayer graphene such an exciting area? It gives us a tunable platform to realize strongly interacting phases. And so, so I've listed some examples of that here. So on the left-hand side is this one of the original papers coming out of Pablo Herrera's group, where they're showing as a function of the carrier density, they're zooming in at half filling, and they can see a variety of interaction-driven phases, insulator phase, superconducting phase, and as well as these metallic phases. And this is something that could never happen in graphene because graphene by itself, because graphene is metallic. On the right-hand side is data from Andrea Young's group, which is showing the quantum anomalous Hall effect. So they're looking at a different filling, which is 3/4 filling. And here they see this quantized Hall plateau, which is zoomed in down below. And you can see these hysteresis loops, which are a sign of magnetization. And of course, again, this is something we never see magnetization in a single layer of graphene. So these are just some of the types of exotic phases that we can see in twisted bilayer graphene that that seem to be driven by interactions. Now, of course, understanding these interaction-driven phases is a real challenge for the field. And so there's been a lot of work in that direction, which is not the focus of this talk. One of the things that I think is pretty well understood is that these interacting phases are enabled because you get flat bands at the so-called magic angles. And so I'll give a little bit of a review of how that occurs. This is predicted by the Bistritzer-McDonald paper from almost 10 years ago. So the basic idea is that if we have these two sheets of graphene and we want to make a low energy model, we don't need to worry about the unit cell, which is absolutely enormous and has many, many atoms in it. But instead, we can just say, well, the low energy physics in graphene is coming from the Dirac cones. So how about we just make a model which couples the K point in one layer to the K point in another layer. And so pictorially, the band structure will look something like this. You have a Dirac cone in these two different layers, and there'll be another half of the model, which is coming from the two K prime points. And these two Dirac cones will cross. Their crossing point is set by the twist angle, because that determines how close the cones are. And once you add an interlayer coupling term, a gap will open, and that will kind of start pushing this lower band down. And so you can see that there's some interplay between twist angle and the strength of interlayer coupling that at some special points will push these bands down exactly and lead to a very flat band, at least which is flat in one direction. One of the points to note here is that people talk about the magic angle, but actually it was known then and is still very well understood now that there's a series of magic angles. And so this is plotted the velocity of the Dirac cone. So velocity equals 0 is what's referred to as these magic angles, and that's where these flat bands are occurring. This is plotted as a function of this parameter alpha, which is W is interlayer coupling, and then theta is twist angle. And these are the parameters in graphene, the velocity and the position of the Dirac point. And so you can see there's actually a series of magic angles, which is believed to be an infinite series. And all the experiments are taking place, most of the experiments are taking place at this first magic angle. That's the largest one, around 1.1 degrees. The others are all smaller angles, which may be increasingly difficult to realize in experiment. Now, the Bistritzer-McDonald model gives some justification for why the velocity might go to 0, but there's still a question, which is why do the bands get so flat? That doesn't explain why you would get a completely flat band. And so in the past, I guess in the past year or so, coming from Ashwin Vishwanath and company, they proposed this chiral model. And the neat thing about the chiral model, I'll explain it, is that it's exactly solvable, and you can show that the eigenstates, you can show that there's a set of 0 energy eigenstates corresponding to exactly flat bands, not the perturbative result that you get from the Bistritzer-McDonald model. And so the model is as follows. So this matrix is kind of showing the Bistritzer-McDonald model I just described. So it'll have top layer of graphene is one Dirac cone, bottom layer is another Dirac cone, and then there's this interlayer coupling. And generically in matrix form, so the matrices are sublattice. So each of these sigma matrices is acting on the A and B sublattice. We can write the interlayer couplings in terms of an identity Pauli matrix and sigma X and sigma Y Pauli matrices. There's not going to be a sigma Z term because the two sublattices are identical to each other. So in the Bistritzer-McDonald model, they set these two coefficients, W0 and W1, equal to each other. The chiral model does something different, which is they set this W0 equal to 0. And so what you're left with is only off-diagonal Pauli matrices, and graphene also, the K dot sigma Dirac cone also only has off-diagonal Pauli matrices. And so sigma Z matrix will anti-commute with the whole thing. And so this chiral model has a special property that is exactly particle hole symmetric because it anti-commutes with the Pauli matrix Z. The other special property, which I already said, is that it actually, the 0 energy spectrum is actually analytically solvable. And you can prove that there's a series of states at 0 energy, which comprise an exactly flat band. So to see a little bit more how this might occur, it's useful to do a basis change. Instead of working in top layer and bottom layer, we can swap to being A sublattice and B sublattice, where within the A sublattice, we have top bottom, and then within B, we also have top bottom. So each of these is now 2 by 2, and you can explicitly see, in this basis, you can explicitly see that this chiral model has no AA and no BB hopping, it's just AB hopping. And so that so this basis makes that explicit, and it also makes the fact that it anti-commutes with sigma Z explicit. So now the 0 energy spectrum is just going to be 2 component spinners, which will either be annihilated by D or by D dagger. And it turns out that these 2 component spinners take this form, which is kind of complicated. The point is just that these exact solutions exist. Okay, so this was work that has been done in the past year or so. So now I kind of want to introduce our contribution to this. So, so the first thing that I'm going to show is an analytical rewriting of the wave function, which makes the connection to quantum Hall physics a little bit tighter and I think a little bit more clear. Then I'll show some numerical results where we look at these higher magic angles that I was mentioning. And then finally explain what the experimental consequences of our results are. And this is a collaborative project, and I think a lot of the credit should go to Ji Wang, who I think maybe I saw in the audience, who's a postdoctoral fellow at the Flatiron Institute. So I first want to review some analytic properties that we derive, which allow us to write these exact wave functions in a slightly simpler form. So the first is that there's an inversion symmetry operator which emerges in the low energy model. This doesn't come from this isn't an exact, this doesn't correspond to inversion on the crystal lattice because inversion mixes two valleys. And right now we're only talking about one valley. So this is a feature that emerges from linearizing the Dirac cone and from taking this chiral model where we set one term equal to 0. But as a consequence of having this symmetry, that means that we can, so I showed how the zero energy wave functions can be written as two component spinors. Now, this means that these two component spinors must be eigenstates of inversion. So this highly restricts the form that the zero energy wave functions can take. And so this spinor part is an eigenstate of the inversion operator, which is polymatrix Y. So that's where the I is coming from. And this eta is just a plus or minus 1. So these are the eigenstates of tau Y. And this G is some function. And this function is going to change at different magic angles. There's also an overall prefactor. It turns out that when we write it in this basis, this overall prefactor is exactly a quantum Hall wave function in the lowest Landau level. So this is kind of why this analytical
Sorry, perhaps a good opportunity to ask a question. So what is the motivation for neglecting hopping within one sublattice? Is this, I understand it gives a nice answer, but
right.
But is it realistic or is it similar to the physical model for some reason?
Yeah, so hopefully I'm not going to get disconnected again. There's a couple of reasons for considering this. So one is exactly what you said. Has nice analytical properties, but there's another reason why you might consider this, which is that the ratio of these parameters W0 over W1 is not small. It's expected to be around 0.7. So taking it to be 0 is not particularly realistic, but it turns out that when you relax the graphene atoms, actually, so I mean, instead of taking two rigid layers of graphene, you allow them to relax a bit. And one of the things that they do is buckle. And the AA regions actually get to be further apart than the other regions. And so that makes you think that maybe this ratio is actually smaller than people originally computed by keeping the layers rigid. So that's one reason to justify it. And then actually a second reason is there's a really neat paper. So I actually was going to talk about this a bit later. There's a really neat recent paper by Oscar Vafek, which they're doing a RG analysis of Coulomb interaction. And there they show that the chiral limit is actually a fixed point. So there's also some thought that you might be flowing into this model. You know, we didn't know that going in. We're interested in it because of the nice analytical properties, but it's definitely, especially when considering the relevance to experiment, it's definitely worthwhile to ask that question. So thanks. Any other
Got it,
questions?
thanks.
Okay, good. So the thing that I was just saying was that one of the things that we can show analytically is that the wave function is going to split up into a spinor part and a quantum Hall wave function. And this makes it very clear why these wave functions have to be Chern insulators, because the quantum Hall wave function carries a Chern number. And this wasn't so explicit in the exact wave functions that I showed on the previous slide, although it was known. But there's one other feature here, which is that the quantum Hall wave function has magnetic translation symmetry, but this whole wave function needs to be a block wave vector because we don't actually have a magnetic field. And so what happens is that this function G has to split. There must be this kind of anti-quantum Hall part in order to compensate for the magnetic periodicity of the quantum Hall wave function. And so actually this function G splits into two parts, which is an anti-quantum Hall wave function happening at a fixed K vector, and then a cell periodic function rho. And so we can now rewrite these zero energy eigenstates as in the following way. There's this spinor part that I was just showing. There's a cell periodic part rho, and then there's an anti-quantum Hall wave function. Anti just means having the opposite Chern number, but that's at a fixed K point. And then there's a quantum Hall wave function, which is at a variable K point. So this is, I mean, so far it's kind of just formalism, but it also allows us to understand the properties of these wave functions in a little bit more clear way. From this, we can see the topological structure of these flat bands. So I've been talking about one zero energy eigenstate, which say has Chern number 1 coming from the quantum Hall wave function, but it has a partner in the same valley. That thing will have opposite Chern number. And then in the other valley, there's two other states which are related by time reversal, and they also have opposite swapped Chern numbers. And so altogether, there's 4 flat bands. This is neglecting spin. 2 with plus Chern number +1 and Chern number -1. And so like in the beginning, I showed some quantum anomalous Hall data from Andrea Young's group. This offers some intuition for understanding that, not completely, which is that in that experiment, it's actually twisted bilayer graphene on top of hexagonal boron nitride. Hexagonal boron nitride breaks the rotational symmetry, so it actually will split these lower 2 bands in energy from the upper 2 bands if we were still operating within our nice chiral limit. And so that would split into only 2 flat bands. And then you can see in order to get anomalous Hall effect, we need to further have spontaneous time reversal breaking in order to break the difference between the K valley and the K prime valley. So I'll now talk about some of the numerical results that we have for this model, which I think are interesting and a little more clear to see. So the first is we can plot the charge density for these flat band wave functions. So I'm looking at a particular K point, the capital K point, and I'm plotting its density, the bottom component of the wave function and the top component of the wave function real space. So now this is a real space hexagon. And one of the features that you can see is that the charge density is peaked at the center. These are the AA points of the lattice. And then these purple points are exact zeros, which are at the AB points of the lattice. And so as a first reality check, we can check that this is consistent with the data for twisted bilayer graphene, which is that charge density is peaked at the AA points. And so this is a few different pictures at different scales from Eva Andre's group. But this is the scale of the moire superlattice. And so these kind of peaks in charge density are corresponding to these peaks. So this is, like I said, this is kind of a reality check that this model is not completely out in left field. Now, the new result from our work, which is not done previously, is we're now looking at these other magic angles. So I said before that there's a first magic angle around 1.1 degrees. And then this is a smaller one. I think it's around 0.5 or 0.6 degrees. And then they get increasingly smaller. We looked at the first 3. And so what we see is that there's this pattern that I was just describing of having charge density maximum in the middle and then having minima at the corners is still kind of there, but you get this increasing structure as you go to the higher Landau levels. And in particular, you get an increasing number of zeros. So these, again, they're all exact zeros. We can check this, we can check it numerically, and we can also prove, for some of them, we can prove that they have to be there. And so you get this structure, increasing structure of zeros, which are happening near the middle of the real space unit cell, and then also around the corners. And then you go to the third magic angle, you get more of these. And one of the reasons that this is kind of interesting is because you would get the same structure as if you compared the lowest Landau level to the higher Landau levels. All the Landau levels have a Chern number, but as you go to higher Landau levels, you get a finer structure, and that structure corresponds to getting more zeros in the wave function. And so this is a kind of interesting connection, which suggests that possibly the interacting phases that you observe, if you could access these higher magic angles, may have a similarity to the interacting phases you could observe at higher Landau levels. And that's interesting because in quantum Hall physics, you actually do observe different interacting states at the second Landau level than at the first Landau level.
Hi, Jen, can I ask briefly what symmetries you're enforcing?
Yes. So this has, I don't think we've sacrificed any of the symmetry of the model. We have C6 rotational symmetry that takes you to the other valley though, so I'm not really talking about that. Within the valley, we have C3 symmetry. We also have C2 times T that would take you from this spinner to a partner spinner, so that also doesn't really affect this picture. And then finally, there's a mirror symmetry, which is why, for example, like these three are flipping, they're symmetric across this line.
You have this like C2X symmetry also, this like layer flip.
So right, so I need to be more careful whether I actually mean mirror or C2X. I think we do have that symmetry because we haven't, so I think we do, but I'm not 100% positive because we haven't had to get rid of any symmetry in order to make this model. Like we haven't von Neuerized it or anything. This is just exact diagonalization and looking at it in real space. One thing I want to say is that this wave function is at the K point, and so you can't see all of the symmetries in this picture because some symmetries will take K to, I guess, to K prime. So this is one of the,
Okay,
good.
thank you.
There was another question. Ridro, did you have a question? I saw your hand was raised for a moment.
Well, thank you, Babak. Mike, well, it's a somewhat, well, let me ask the question anyway. We know that if you take a crystal structure and you go to higher and higher block bands, the periodic part of the wave function, of course, will develop more and more nodes, right? So is there an analogy with what is happening there and this multi-nodal structure that you see when you go to higher and higher magic angles?
Right. So, oh, sorry, is there a second part to the question?
Oh, no, that was my question.
Okay. I didn't know if I cut you off. Right. So that, I think, so there's some kind of very rigorous theorems, which I certainly don't know very well, which are basically saying that this is a general feature. You know, we're familiar with this from the quantum harmonic oscillator. As you look at higher levels, you get increasing zeros. And there's some mathematical theorems which tell you conditions when this will happen. If you have this kind of differential equation and you need some properties, then you will get more zeros as you look at more solutions. So one of the things that we did here was try to make an analogy to the quantum harmonic oscillator by looking, basically just by making this, by looking across one 1D line. So turning it into just that 1D problem. And what happens is we have real and imaginary parts of our wave function. So we have two components and real and imaginary parts. So it's not an exact map, but if we kind of pretend that if we impose some extra constraints, then we can map to that problem and we can understand these extra zeros in that way. So we haven't done it rigorously, but my intuition is that the fact that we're seeing increasing zeros is actually a very common fact of solving a common situation when you solve a differential equation, that you're going to get increasing zeros in your family of solutions.
Thank you.
Yeah, thanks.
Okay, Jennifer, I'd want to ask a quick question also.
Great.
Is this relationship between the higher magic angles and higher Landau levels an analogy, or is it more mathematically precise? Like, is there such a thing as Landau level mixing, for example?
Oh.
Because that can often influence the physics in, you know, different Landau levels.
Mm-hmm. Right. So I guess I would say I am more, so I don't know the answer to that. What I am more concerned about with the connection to the quantum Hall physics is that there's differences because we have this kind of extra spatial structure on, actually it's more severe than that. In quantum Hall, you have a uniform magnetic field and you have a uniform Berry curvature. And here, because you are a churn insulator, you don't have, this is not uniform, you have very strong fluctuations. So that I think would be the thing I would worry about more in the connection to quantum Hall physics. Yeah. Okay, the question of Landau level mixing may be, I'm not positive about, yeah, I'm not sure about that. I guess what I'm wondering is if we move away from the magic angle, these solutions no longer become precise, or if we move away from the chiral limit. And so that may be kind of an analog to Landau level mixing. But yeah, I'm not sure. I don't think that the relation is, as precise as, I would more prefer to call it an analogy. But
Okay,
but what is precise is you have a series of bands with a churn number, and then you have extra structure on top. So that's definitely the analogy. Yeah.
Okay, great. Thank you.
Yeah, thanks. Okay, great. So the other thing that I want to say, so what I was just saying was that if we go to higher magic angles, we get an increasing number of zeros. And I was previously plotting this at the capital K point. I'm now looking at a generic K point, lowercase k. So this picture is slightly different than the others and slightly less symmetric looking for that reason, because I want to show some generic features of these zeros. So we can, so first off, some of the zeros move around as you look at the wave functions at different K points, they move around in space and others stay fixed. And actually there's only one that moves around. And this is actually something I didn't know about, which is it's a generic feature of a quantum Hall wave function, which is that if you look at a quantum Hall wave function, if you look at each wave function psi of k, it'll have a zero and in real space. And if you move around to different k's, that zero moves around and covers the entirety of the unit cell as you scan around all the k's. And that's the same thing that happens here because we have this product with a quantum Hall wave function. So this zero is coming from the quantum Hall part. And as we look at different k's, it moves around. Then there's these other zeros at the corners. So this one, those are all part of the same. They're coming from the anti-quantum Hall wave function. Since it's at fixed k, those don't move around. That's what there's a quantum Hall wave function at fixed capital K. So those just sit there at the corners. And then finally, there's these other zeros. These ones are also, they come from the prefactor rho. And these ones are also fixed for all k. And these are the ones that change as you go to increasing magic angles. So this part of the wave function, this part of the wave function are the same for all magic angles. And this first function rho is changing at different magic angles. There'll be a different function rho that solves the equation, and it has a different number of zeros. So these ones are fixed for all k, and they're coming from rho. The other thing that we can do, since this is a zero in a complex, one component of the wave function is a complex number, it goes to zero. So we can classify these zeros by a winding number. And so on this right-hand side, I'm showing all of the zeros. Each of these purples is mapped to one circle, and it has a plus or minus sign corresponding to a plus or minus winding number. In principle, a winding number takes on integer values, but here we only see plus or minuses. And so it happens that the zeros near the origin seem to always have the same chirality, and the zeros at the boundary, the ones that are increasingly appearing, which are the red ones, those also have the same chirality. And that's just something that we observe numerically. And so I can now say that there's some of the experimental consequences that I would expect from these observations, which is, one, there's a pattern of charge density. If you could access the higher magic angles, you could literally look with STM and see these zeros occurring. So there's a charge density signature that, that we predict could be visible in STM. The second signature is that this clustering of zeros with the same chirality indicates that the wave function is going to be winding around these zeros. And since you get more and more zeros at higher magic angles, that winding is going to become bigger. And so we predict that there is some kind of orbital current which would become enhanced as you go to higher magic angles. And so here we've written down what this current is and we've plotted it. And so you can see, if you compare the first to second magic angles, you can see that the magnitude of this current or its phase winding becomes larger.
There's a question in the audience.
Great.
Tobias?
Yes, coming from an experimentalist's viewpoint, do you have any idea how stable these effects are against reconstruction of the lattice? Because as we go to smaller angles, there's more likely to reconstruct to Bernal stacking, of course.
Right. So okay, so that kind of comes down to our original model. Now, it seems like what you're describing is going to be an obstacle to observing the second magic angle at all, because it may just kind of disappear and relax into AB stacking. So what I think is that if you can't access that magic angle, then we're not going to be able to make any predictions about it. On the other hand, if you, like, for example, people have studied the relaxation of atoms away from the rigid bilayer graphene, and that's going to just change some terms in the Hamiltonian, but it shouldn't nullify these effects. And in fact, the zeros, because they have this winding, are actually robust. So even if we move slightly away from this chiral limit, we should still be able to see these zeros. So I think if you are near this chiral limit, but even if you're not exactly at it, and if you can access these increasing magic angles, then I have faith in our results. But I'm not going to make it, we haven't done an ab initio calculation which would predict the stability at the other magic angles. Okay.
Because
I guess one of the things, yeah, go ahead.
What happens typically, or what we observe, is that the AA sites stay in place, but locally it rotates back into Bernal stacking. Mm-hmm.
Yeah, so, okay, so I guess you raise another interesting point, which is that you can also have disorder within the angle. You're realizing different angles at different point in the lattice, and that I'm not going to say anything about that. Yeah.
Yeah.
Oh, right. But the other thing that you made me think of was that, there are other platforms besides twisted bilayer graphene. The most simple, well, I don't know if simple is the right word, but one is, for example, in Corey Dean's group, they apply pressure and then they realize the magic angle at a slightly higher angle. So there's ways to tune where these angles appear, which might make them more stable. And then there's also, of course, different material choices. And so in principle, there could be a different material where the first magic angle, say, was at 5 degrees, and then the next was at 1 degree. So, so even if it doesn't turn out to be the right platform here, there could be some hope of realizing these angles in other material platforms.
Thank you.
Yeah, thanks for the question. Okay, good. So the last point that I wanted to make here about potential observables, now this is getting more, even more hypothetical, is that this connection between higher magic angles and higher Landau levels. And the only point that I want to make here, which I may have said earlier, is that you can see different phases in the first and second Landau level. different interacting phases. And so you might hope then that there'd be different interacting phases at the second magic angle rather than the first magic angle. And that's kind of an interesting reason to explore these different magic angles. Okay, and this actually addresses the point that Anton asked in the very beginning, which is why should we care about this limit and why should we think that it's physical? And so I mentioned these points earlier. I'll say that although this ratio is not close to 0, it may actually get closer because the layers, they do buckle, and that buckling actually favors a smaller ratio because the buckling is largest at the AA stacking points. There's also a really neat recent paper by Oscar Vafek showing that this chiral limit is a fixed point. So possibly systems are flowing into this model. And then the other point that I want to make is maybe it doesn't really matter for what I've said so far. Like these zeros are robust to small perturbations, and same with kind of any sort of circulating current is going to be robust to a small perturbation. So we might hope that these observations will persist if we are nearby this limit. Okay, good. So that is everything that I wanted to say about this first part of the talk, which is mostly the entirety of the talk. I would like to at least maybe I'll spend kind of the next 10 minutes going over the next part of the talk, unless there's any pressing questions, and then take questions. We can have more discussion at the end. Okay, so I'll just give a brief overview of the second idea, which is is there a question? Okay, sorry.
No,
So
I didn't see any questions.
Yeah,
go ahead. Sorry.
Okay, good. Great. So the second idea that I just wanted to bring up, because I'm also kind of excited about this. So this is a collaboration with this team at Rutgers, and so the basic idea is that I've been talking about twisted bilayer graphene and variations on twisted bilayer graphene. What would happen if we use the Dirac cone on the surface of a 3D TI instead of the Dirac cone in graphene to make a twisted heterostructure? And so the natural question to ask is, why would we want to do this? And the reason that I would want to do this is because in twisted bilayer graphene, we realize some interacting phases, in particular, say superconductivity. And if you realized if you had the same superconducting instability on the surface of a 3D TI, then we know that you would get a topological superconductor. So the idea is that maybe some kind of twisted heterostructure on the surface of a 3D TI could be a tunable route to interacting topological phases. That's the motivation. And then the next question is, would you actually expect this to happen? Okay, I don't know, but what we do know is that there's been some work around the beginning of the field of when 3D topological insulators were discovered. People did a lot of different calculations, I think mostly using mean field theory, looking at these interacting instabilities. And so the bottom line is that people have looked at superconducting and magnetic instabilities from a mean field level. And as usual, all of these instabilities are enhanced if you have an enhanced density of states. In other words, if we could flatten the Dirac cone on the surface of a 3D TI, then that would increase your chance of getting into this phase if you trust the mean field theory. So I think that gives us at least enough motivation to ask, well, can we get flat bands on the surface of a 3D TI if we make some kind of twisted heterostructure? There's one major difference with twisted bilayer graphene, which is that on the surface of a 3D TI, you can't get flat bands that are isolated in energy. So in twisted bilayer graphene, you have these really flat bands, and there's a small gap, very small, around 10 MeV above and below the flat bands. On a TI surface, you're never going to open a gap. That's kind of a fundamental property of the bulk boundary correspondence. So what we do in this work, which I'll give a brief overview of, is look at the band structure effects of having a moire superlattice on the surface of a topological insulator. We don't study the interacting instabilities. We're just looking at the band structure, trying to see, can you actually get flat bands Yeah, and the other thing that I want to say is, well, okay, what are the different physical ways that we can realize this? I have two different ideas in mind. So on the left-hand side, this crystal is meant to be bismuth selenide. And what we're doing, what I'm thinking of is applying a modulating potential on one of the surfaces. And so there's been some experiments on this. They have some dielectric silicon dioxide, I think. They drill holes into it. They put a gate below that, and that creates a potential which is spatially varying. And the spacing, the length scale of the spatial variation depends is a feature that you can make by changing this device. The other idea that I have is what I call a twisted heterostructure, which is just suppose we have a block of our 3D TI, we put a 2D insulator on top of it, and then we twist these things. This is obviously a mock-up of twisted bilayer graphene. And one of the things that we show in our work is that if this 2D material is an insulator, and if it's exactly lattice matched, which is a big if, then you can integrate out the degrees of freedom of the 2D layer. You can always do that. But the point about the lattice matching is that you can make a small angle limit and get a moire superlattice exactly in the same way as twisted bilayer graphene, and you're left with a slowly varying potential, which is kind of the same Hamiltonian as you would get in this left-hand picture. So these are two different physical realizations which give us the same Hamiltonian, a 3D TI, and some slowly varying potential on top of it, which has some very large length scale, and that's what we call moire superlattice potential. So this is the Hamiltonian that we study, and there's 3 different ways that we look at this Hamiltonian. The first is a continuum model, kind of like the Bistritzer-McDonald model. And then we back that up with some 3D models, a tight binding model and an ab initio calculation. So I will kind of just give a flavor of how this works, which is, this is using perturbation theory. We can make the analog of the Bistritzer-McDonald model and calculate the change in velocity for small twist angle. And so if V is your initial velocity, V star is the velocity that you get with this superlattice potential. And what happens here is that V gets divided by this factor 1 plus alpha. Alpha is positive. So you can change the velocity of the surface Dirac code, but there are no magic angles. In twisted bilayer graphene, V star can be equal to 0 because this function is a little bit different. So that's the first feature, which is different than twisted bilayer graphene. The other feature, which is different, is that you can compute perturbatively. So if you look at the density of states, usually a Dirac cone makes a very sharp V here. But what happens once you add the superlattice potential is you get all these dips. These are coming from satellite Dirac cones, which are because you have different momentum coupled by the potential. So on the left-hand side is a Dirac cone. On the right-hand side is showing if you have a potential, you will open up gaps in this spectrum. You'll basically fold the Brillouin zone over a bunch of times and open gaps. And we can use perturbation theory to find the position, the energy and dispersion of these satellite Dirac cones and figure out, we can map them exactly to these dips in density of states. But the important point is that the satellite Dirac cones can't gap because they always come from time reverse partners. And so this is coming back to the original point. You can't get a gapped flat band on the surface of a 3D TI the way you can get a gapped flat band in twisted bilayer graphene. So, so then the concern that you might have is, I've made some claims very quickly in a 2D continuum model. How does this hold up? Because the continuum model, I glossed over this. I'm just assuming a linear Dirac cone. So it ignores the higher order dispersion that you would see in, for example, bismuth selenide, and it also ignores the coupling to the bulk. And so, so we study some 3D models in order to show that these results are actually somewhat generic. And so, so I'll kind of skip over some of these details because I want to show the numerical results. So this is a 3D TI with a superlattice potential on its surface. This is a plot of the velocity of the Dirac cone as a function of the potential strength. And so this is showing the Dirac cone renormalization. So perturbatively, we had this result where the velocity gets renormalized, and this function alpha gets larger with smaller twist angle, and it also gets larger with larger potential strength. And so as we tune up the potential strength, we eventually see this Dirac cone velocity start to dip down. The dots are exact numerical results, and the line is our perturbative result. We had to go to high orders in perturbation theory in order to fit these lines. So that's something which is backed up by our numerical model. And also, as I said, the velocity never goes to zero, and numerically it seems to hit a minimum and then come back up. So numerically it's not going to zero either, even if we go beyond perturbation theory. And then these are the velocities of the satellite cones. And the point here is just that we can track them, and they agree with perturbation theory. And actually some of these perturbatively do have a magic angle, but numerically they avoid going to zero. So it seems like these things never really want to get perfectly flat. And then this is kind of the same plot as a function of twist angle. So again, I'm plotting velocity of the Dirac cone. As we make the twist angle smaller, the velocity is getting smaller. This is the limit of the size of the supercell that we could consider. And the perturbation theory predicts that it would keep dipping down to some point and then kind of saturate. And then these are some plots of the band structure. And so one of the other things that can happen is that multiple satellite cones can align with each other. And that's one way that we can get very flat bands that we weren't expecting. So going into this, I was thinking, can we use a potential to flatten out the original Dirac cone on the surface of a 3D TI? And it seems like that's actually not the most promising route. What is more promising is that as you turn up your potential strength, these satellite cones all move around in energy, and you'll pass through places where they align with each other. And that seems to create a flat band and a peak in the density of states, which is more pronounced than that coming from the original Dirac cone. And then just to wrap up, the other thing that I want to say is that we did an ab initio calculation having a superlattice potential on the surface of bismuth selenide, and we can actually still see some of these results, which is kind of encouraging. And so this is plotting the satellite cones in energy, but on the right, I'm plotting the velocity of the original Dirac cone in red. So we actually see this thing dropping down in velocity as we turn up the strength of the potential. And then these are the satellite cones, and okay, it's hard to see what they're doing. I think the most salient feature is looking at this one, but this satellite cone is very interesting. It actually starts out with zero velocity. This is a feature of the hexagonal lattice that didn't happen in our, the previous model that I was showing was actually on a square lattice. And we can understand using perturbation theory why this occurs, because we can actually pick out the satellite cone is coming from 6 different momenta, which are mixed by the potential, and they all pair off into time reverse partner pairs. And this pair has angular momentum that differs by more than 1, so they don't end up having a linear term in the dispersion. So this is another way that we can get a flat band, albeit not at zero energy, coming from these satellite cones. So that was kind of a lightning fast summary of this work. I think that the main result that I want to say is that there's 3 different ways that we can get flat bands, flatter bands on the surface of a 3D TI. One is renormalizing the original Dirac cone. Another is what I'm showing here, having different satellite peaks align with each other in energy. And then the third is the feature that I just said, which occurs on the hexagonal lattice. You need to have more than a 4-fold symmetry, which is that the satellite cones can actually have zero velocity to leading order. And that point is actually discussed in another recent paper on the archive by Liang Fu. They call these higher order Van Hove singularities. And it seems like these satellite cones, which have vanishing velocity, in their work, they show that the TC is going to scale polynomially rather than exponentially with the phonon, electron phonon term. And so that actually may end up being a promising place to look for interacting physics on the surface of the 3D TI in these sorts of systems. Okay, great. So after that, are there any, this is kind of the stopping point that I want to reach. Are there any questions on either part of this talk?
Okay, I see a number of hands raised. First of all, thank you, Jennifer, for great talk. Anton, you can go ahead.
Yeah, so I wanted to ask whether all flat bands are equally good. Say, it's well, first of all, since you are considering a system with a topological surface with unbroken time reversal, then of course every single band will look like a Dirac cone, right? They have to wind all the way from negative to positive infinity. So now some of these are probably say now if I were to imagine how to make flat bands completely by hand, I could create say potential wells that trap long-lived resonances. So these can never be fully isolated once again because these are topological insulators. But I can imagine making a tunnel barrier where a state bounces around and through that has a very small coupling to the next unit cells. But that seems to be like a boring flat band where all orbitals are localized. And I thought that twisted bilayer graphene is more interesting because it's not fully localized and there the band flatness comes from a different origin. So do you have any considerations here? What kind of flat bands are those?
Yeah, so that's a really great point. We can make flat bands in extremely trivial ways by making a very huge lattice, imagining a crystal with a huge lattice spacing. So I think that, but I actually don't know a good way to categorize which flat bands are interesting and which ones aren't. I think that Berry curvature is something which is probably going to be interesting. And I guess what I would hope here is that since we're near this Dirac point, and we know that the Dirac point on the surface of the TI is highly delocalized and not corresponding to some kind of very local trivial state, I guess I would hope that these would fall into the interesting category. Yeah, but I don't, okay, so that's one thing to say. I guess there is another thing to say, which is we could look at the ratio also. Depends on what you call interesting. You might just think that interaction-driven phases are going to lead to something interesting. And I guess we could look at the ratio of like Coulomb energy to kinetic energy. And if we took our hypothetical crystal, which had a very large lattice spacing to make very flat bands, well, the Coulomb energy would also be very small there because the electrons we might expect would be very far apart. So I guess, yeah, that could be another way to quantify this.
No, but of course, so a large lattice constant only makes doesn't make bands flat relative to level spacing. But I imagine a strong confining potential would, on the other hand. Mm-hmm. So if you want to diminish velocity, to reduce the velocity, you want to almost localize some bands, and this is also I think a bit what you see in your dispersion relation. The satellite Dirac cones are localized, and there's one band that goes through the potential due to the topological properties, I'm guessing. And also to a bit say, I'm also not sure what makes flat bands interesting, but that's why I was wondering about your considerations there.
Yeah, I think our consideration is the original thing that I was looking for was, can we renormalize the original Dirac code? Because as I said in the beginning, we know from a mean field effect that is more likely to lead us to interacting topological states. That's really the thing that I am positive is interesting. And then I can also kind of point you to this paper by Liang Fu, which is suggesting that having a flatness in some of these satellite cones may also be interesting in the sense that it can lead you to TC, which has a better scaling relation. I think it's a very important question. What is the general criterion for when flat bands are interesting? Because you see a proliferation of papers on flat bands in our field, and I'm now contributing to this, and it would be great to quantify that better. And I've copped out of that question.
All right, thanks.
Yang Ji.
Hi, Jennifer. So my question is about in this in your calculation, you don't find the velocity go down to 0. I'm just curious, what is the difference between your model and the Bistreet McDonald model and those model Jed and Will Justin they work on, including myself. I'm just curious why there's no 0 velocity.
Yeah, so I think the reason, the major difference between these models is that in the Bistreet McDonald model, you're coupling 2 Dirac cones. Here you have 1 Dirac cone and you're putting a potential, it can only couple to itself. And so I think that's crucially different. I think that also if you took actually there's been experiments in Corey Dean's group where you have a single layer of graphene and they put a superlattice potential on that. And I think that that is probably more similar to this. So yeah, I think there's a very big difference between a single Dirac cone and having 2 Dirac cones. So
just follow on that, because I worked with Jed and Justin previously. So at this minimum value of the velocity, I'm just curious, did you look at the momentum space wave function and the structure of the wave function? Because that's how we previously identified the origin of the magic angle phase.
Okay. I'm sorry. Do you mean actually, let's see.
So you have this nice comparison perturbatively and numerically, yes. So you don't find it go to 0, but you find a minimum.
This point here.
I'm just curious if there's something special at that minimum. Hello?
Yeah, I think I lost you at the,
sorry.
at the end of that.
Okay.
But I think I got the gist. So you asked if there's something special happening at this minimum.
Yes, I'm just curious.
Yeah. Yeah, we did not look, we did not look at these, we did not look at the eigenstates corresponding to this point. So what we did, like we looked at the density of states to pick out kind of to pick out the velocities, but we did not actually look at the eigenstates. So I don't know if there's something, I don't know if there's something special about that. That didn't occur to me. That didn't occur to me actually. I guess what I did think was that even in the Bistreet or McDonald model, for example, the velocity gets smaller and bigger and, it has some oscillating structure. So I guess I just assumed that it, that it would also have some oscillating structure here. But no, we didn't study this. I don't know why that minimum comes. The solid line is 5th order in perturbation theory, so we didn't go further than that. It would be interesting to know if there's some structure or pattern and if there's like a series of minima, that would certainly be interesting.
Okay, thank you.
Yeah, thanks.
Okay, I see another question by Benjamin.
Hi, Jen.
Hey, Ben.
Thanks for the nice second part of the talk as well. So I have a question about your statement about the number of Dirac cones. So you suggested that having an even number may help, but so what do you think would happen if you had, say, like 2 from some TCI phase? Do you think like the spectral flow is still a major issue, or that you could rectify some of the obstructions or obstacles you have?
Right. So I guess what I think is that you need to have 2 at similar momentum. So if you have 2 Dirac cones on the surface of it, so that's an interesting question. Could you put a superlattice potential on the surface of a TCI? It would fold up the band structure and you could make it so that your 2 surface Dirac cones were nearby each other. And then they would in principle couple. What I think the problem there that's going to happen is that originally they're far apart in momentum space. And so like that original spacing means that the coupling term will be small. That's like just like the 2 valleys in graphene are kind of separated because they're originally far apart. So my suspicion is that the better idea would be to take 2, say 2 weak TIs and put them on top of each other in relative twist, and then you would have 2 Dirac cones that are nearby each other. I think on one surface, they're originally going to be too far apart to have a significant effect. That's just a guess.
Very, very briefly, because I know other people might talk. Why do you distinguish between, like, what do you think is special about a weak TI versus a TCI? I didn't quite understand.
Oh, no, I meant weak TI or TCI. I really meant anything that has multiple Dirac cones.
Okay.
I was just saying Dirac cones that are far apart, they're going to technically be coupled to each other to some order in perturbation theory, but I suspect it's going to be small. So I was just saying, if you have two, I'll just call them topological surfaces, however they may be, so that you have a Dirac cone on one layer and a Dirac cone on another, and then they're separated by some small vector, then some small momentum, then I think that that would be more promising than just looking at one surface.
Okay, cool. Thank you.
Okay, great. So just, I think we're gonna, I don't see any other questions. We can stop the question period. We were hoping to, Yangji, do you have another question?
Yeah, so it's about the first part, because it's long question, so I want to wait until, yeah. So I'm just curious about this interest in finding higher magic angle. How do you think that can help us to understand like the minimally twisted graphene close to the putative magic angle? Because there, I know there you need to consider perpendicular electric field to gap out the AB and BA regime. But I'm just curious, since you have this very nice analog between the quantum Hall and the higher magic angle, and in principle that should apply to very small angle. I'm curious, based on your theory, will you expect anything overlook in that region with an electric field?
Okay. So you're asking what happens if I look with an electric field at the higher magic angles? Is that?
Yes. Yes.
Okay. So, right. The electric field is going to break the symmetry between the two layers, perhaps dramatically, I would expect, because the field, and so that's kind of the picture in regular bilayer graphene. When you apply an electric field, you break the layer symmetry. And so that's actually pulling you far away from the chiral limit, because here in the chiral limit, we actually don't have any sublattice diagonal terms. And so a potential would be diagonal and sublattice, and it would be, I would call it sigma z. It's separating the two. I'm sorry, I meant to say layers. I'm sorry. It would distinguish between the two different layers. So I think that I think it would be interesting. I think that's an interesting term to consider at these higher magic angles, but I'm not sure that this model is going to be so insightful, because I think that it's actually going to be kind of competing with the chiral limit.
Yeah, so if we don't consider the electric field, I think we still sort of expect that a real space structure should show this triangular pattern for a very small angle. I know because you don't really consider the full relaxation, so you probably will be rounded. But I'm just curious about, like, maybe let me ask it this way: what would you expect the real space structure based on your theory in the higher magic angle, maybe?
The real space structure with electric field or without?
No. Just forget about electric field.
Yeah.
For the moment.
So these pictures are actually the real space structure of specific wave functions. So it's like I'm taking the wave function at k, but I'm plotting it in real space. And I guess I should have said this more clear. So some of the zeros, like these purples, they don't move around in momentum space. And so we'll see these same zeros for all the k points. And so therefore they will also be zeros in real space. And so that's why I think that these patterns of zeros will be something observable with STM. I think that they're also going to be zeros in the real space wave functions.
So sorry, let me try to understand this. So the zero, they are in the AA region or AB or BA region?
Yeah, so the center is AA. So the exact center, let me go back to this picture showing all of them. So this is the first magic angle, and here it's a peak, and this is the AA peak that that's been observed in experiment. Then what happens is that the AA peak kind of splits, and you get zeros in the middle, but the peaks kind of move out, and you kind of, it forms like a ring-like structure. Yeah, so these pictures are in real space.
So it's indeed quite different from the real space structure of the small energy angle. Okay.
So that's what the prediction would be. If you could really access these, and as we discussed, the stability is a big, problem. But if you could really access these, the prediction is that if you look with STM, you would see significant differences in the spatial structure.
I see. Thank you.
Yeah, thank you.
All right. Thank you. And thank you, Jennifer, for a great talk. I think